Alrighty. So we're going to talk about memory in C. So I have a few things to look at, which is essentially, you've seen null. Null is typically defined as something like this: void pointer 0, or I've made it as hex 0. This down here is memory. So, and this is very fictionalized. Fictitious? 0 is here, it's the first thing, so null points at this. Nothing else can use this piece of memory. Anything that tries to use this memory will actually cause the program to crash if you use it for anything other than comparison, essentially. We then have two areas of memory, the stack and the heap. And I've arbitrarily said that the stack starts here and it ends here. So that's the memory reserved for the stack, and that's memory reserved for the heap. The heap is accessed through things like malloc, cloc, realoc, and free. And the stack is where your local variables go. Local variables parameters, basically anything that you can access inside of a function. There's also some memory reserved for global variables as well, but we won't worry about that. This is another part. So malloc grabs memory from the heap. Cloc grabs memory from the heap and zeroes it out. Realoc changes the size of memory that you've allocated. Personally, I don't like using realoc if I can avoid it. And free releases any of this memory here. So my reason for not liking realoc is if I didn't know how big it was to begin with, I should be using like a linked list. Well, you can play along at home with the C programming. So that's the general gist of memory. Every program starts at 0, which is odd considering that your computer has tons of memory, right? The one I'm on right now has like 64 gigs. So why do they all start at 0? They don't actually all start at 0. Your program just thinks they all start at 0. Each program has an idealized piece of memory that, from your point of view, starts at 0, but you're given a chunk of memory. Also, that chunk of memory that you're given for your process is generally secured from something else. So if you try to go outside of memory and access what you would think would be 16 and try and access that piece of memory, your program is going to crash. Okay. Keep that in mind because later on that's going to be important. Okay. So null, typically the first part of memory. Anything outside of your address space will generally cause you to crash. Memory in your program, everything starts at 0, though it doesn't really. That's virtual memory, or virtual addresses. And the memory is broken into two areas: the stack for things that are inside of functions, and the heap for things that live outside of functions. That's all there is to know about memory layout, but that's it. If you're getting deeper into how your processor actually deals with things and what's the most optimal way to lay out memory to ensure that you don't have cache misses and all that kind of stuff, then you're starting to dig into architecture, and that's a whole other thing. And the nice thing about C is that it is a low-level language, but it works at a high level. So originally you wanted to program a computer, you were playing with like physical hardware. Then we moved into playing with assembler language. There's some steps I skipped there, but we moved to assembler language. Every machine has a different assembler language. So an ARM chip versus an Intel chip, totally different assembler instructions. What C does is it exists above that so that you can abstract what machine you're working on, and the compiler generates the appropriate instructions and deals with all this memory layout and everything else like that. So we exist at a pretty low level, but we're higher than dealing with a particular type of machine. When you're thinking about things like cache and all that kind of stuff, you're dealing with the actual hardware, and it's you're making decisions not based off of the portability of the language, but you're trying to do tricks of laying things out, knowing how the compiler works, knowing how the architecture is, and all that to optimize things. Generally speaking, most people don't deal with that. And quite often the way you want to deal with that is dropping to assembler anyways, but way beyond the scope of this. So let's take a look at some, oh, I put that in the wrong place. Move this up here. Let's take a look at some code. So first off, we've got main. It's a function, returns a value, all that. Great, cool. Let's just make a variable. I'm going to deal with this memory, and I'm going to deal with it as a very idealized form of things. So we're using POSIX, so a char is 8 bits. 8 bits is 1 byte. Okay, so in C, ISOC, a char is 8 bits or more. In POSIX, a char is 8 bits exactly. So our machine is 8 bits exactly per cell. And that's very common. We're going to say that on our machine, actually, I'm not going to say. What I'm going to use is these types. So one of these things down here, one of these square brackets, is 8 bytes. So a uint8t, that's an int that takes up 8 bits, is 1 cell. 16 takes up 2 cells. And 32 takes up 4 cells. Depending on your machine, you might have a 32-bit machine, you probably have a 64-bit machine. So an int, when you say int, you're saying 64 bits. I'm using these particular weird ones, the uint number sign t, because I want to force the compiler to put things in a certain size. So that's a choice I'm making. So we're just going to use uint values for this, which means I need to bring in standard in and spell it correctly too. There we go. So what this does in the compiler is it says, I'm going to allocate memory, and this is going on the stack, and I'm going to put it here. So this is where I points. Now here comes the fun thing. Let's print out, we'll just do printf. I'm going to cheat, because it's just quicker. I shouldn't use %d. There's a proper way to do that. I'll cover that another day. So we're just going to print out I and see what it prints out. So on this machine, it prints out 0. And if I run it, it's probably going to keep printing at 0 forever. However, that's just by random chance and the way this particular operating system works or this particular compiler works. Typically what happens is memory winds up having random values in it. These are all supposed to be between 0 and 225 or 255. So it's going to be I'll just do that. So it's an unknown value between 0 and 255. Right? For all of these, we don't know what the values are. Which is why sometimes you will, when you go to print out I, you will get some weird value. You don't know what it is. Okay. So in this particular case, it seems that the system has initialized this to 0, but that's not going to be the case in all platforms and all that. You will also, if you set up your compiler correctly, get a warning message saying, hey, you're using I without having initialized it. So what we need to do is say I is assigned 7. Oh. Right. And then when we do that, we're just saying I, which is at memory location 1, is going to get the value of 7. Now when we run it, and we assignment not minus. 3 times wrong. Now when we run it, we get 7. What printf is doing is you've passed in I, so when it sees the %d, it says, okay, I need to go look at what variable that is. Well, it's I. It doesn't know I. What it gets is a memory location. So it's looking at, tell me what's inside of this memory location, and it gets 7. If we make another variable, and make it 2 times I. All that does is, this here, j is assigned 2 times I, it goes, the compiler says, okay, well, I'm going to put this in here, so this is where j is pointing to, right? That we know what j is pointing to, that memory location, here, when we made the variable declaration. The compiler had to lay out the memory and say, this is where j is. That has a random value, 0 to 255, and we're going to do an assignment. We're going to assign the value of I times 2. So the compiler has to say, okay, well, give me the value at memory location 1, which will turn out to be 7 at runtime, and multiply that by 2 and store it into j. So we got 14. And then we get the 7 and the 14. So that's all well and good, but let's try something a little bit different. Let's make a pointer to I. So a pointer says that it's going to be pointing at a memory location. So if I run this now, we're going to get something a little weird. No, we got 1 this time. Interesting. And if I want to set it, I don't say I is assigned 7, right? Because what happens in here, and it just happenstance, but what happens in here is that the value inside of here is 1. But that's actually, I'm going to put in square brackets here again, or I'm going to put in parentheses maybe, round brackets, that this is an address. So what's pointing in I is actually an address. So what we are seeing is that it's pointing to 1, right? What that means is, and we won't say it's pointing to 1, we'll say it's pointing to 2. What that means is that it's actually saying when you go to use this, we're actually going to be modifying what's in cell 2 here, because the memory location is 2. So it's a way of indirection, right? This is a pointer, it's pointing to some other piece of memory. Right? So if I say pointer I is assigned 7 now, it crashes with a sigsev. Why did it crash? Because I don't own memory location 1. Memory location 1 is outside my allotted memory for my process. So it crashes. The problem is that this is pointing initially, remember this is some random value, so this is pointing to somewhere in memory. We don't know where. And it can be any value between 0 and 255. Our values only go from 0 to 15. So if it's 16 or higher, it's going to crash, is essentially what's going on here. Remember, I'm simplifying this significantly. Your memory is much larger. You don't have to worry about this. But that's the idea. So the problem again is we haven't initialized where I is pointing to, and that's where malloc comes in. Now, it's suggested that you cast the result of malloc. You don't need to, but there's a security reason for doing it. I don't remember what it is off the top of my head. And you have to say how much memory I want to allocate. You can actually specify uint, but actually what I'm going to do is I'm going to specify, actually I'll keep it as uint. We'll keep things straightforward. It's unhappy about casting it to a smaller value, but that's neither here nor there right now. It should be fine. And then I can say pointer I is assigned 7, and we're going to print out pointer I, and it still crashed. Oh, sorry, this should be a size of a pointer. Well, I'm just having a bad day all around. There we go. Doesn't like the cast. I don't normally do a cast, so. So now we've allocated a chunk of memory, right? And now, so what happens is this will actually say, because it came from malloc, this now has to be in our heap, which we said started between 8 and F. So this now gets a value of 8, and this is where pointer I goes, to here, and we set it to 7. So when we say I, when we say I, we're referring to this memory cell. When we say pointer I, we're saying go to this memory cell and grab the value, or set the value. So we're interacting with that memory cell. So that's the whole point of pointers, okay? That we can specify memory exists dynamically, and that we don't access that memory directly. Why is this useful? Useful for a number of things, but the simplest one is when we deal with something like a char. We'll do a char pointer, a string. And I'm going to do you're going to do another function called stirdup, which does malloc and a copy. So we're making a copy of the string hello, and it allocates that in the heap. So to look at this, what we have is, this is where S is pointing. And S has a value of H, E, L, L, O, oh, not O, O, and /0. And this becomes a little more complex, but we'll get there in a second. So now our memory looks like this. So when we did stirdup, it said, okay, I'm going to malloc some memory. I need to malloc enough to hold the characters that you've passed in, plus the null byte at the end. That's how a string ends in C. So it allocated all of this, this memory and copied in the values. And then we say we're going to print out a string, and we're going to pass in S. Now S is strange, and I'm going to pass it in a little bit different. We're actually passing in the address of S0. So we're passing in the address of S0, which is this memory location here. So we're passing it this memory location, which is the same thing as if we just said pass in S. It says, well, that's memory location 8, so I'm going to use that. So rather than the function receiving as parameters the letters HELLO/0, which would be quite expensive. Imagine if you had a huge string, right? That would be very expensive. I'll explain why in a second. But now all we're doing is passing the address of the first character of the string. And what printf does is it prints out each character until it finds the null byte, and then it's done. Which is why you need to remember to make sure you add room for your null byte and to set the last character to null. If you don't do that, it will continue printing out random garbage until it happens to, at some point in time later, encounter a null byte, or it goes past the end of your memory, right? Which can be disastrous if here you have world, right? Because what you'd be printing out if you forget the null byte, you'll print out hello, some garbage character, world, and then null byte, when you only meant to print out hello. So that's why that null byte is very important. So why did I say it's expensive? Well, remember what I said was that local variables, parameters, right? What's a parameter? This is a parameter. So if we passed in the letters HELLO, we'd have to push each of those onto the stack. So they'd take up room in here. Not only would they take up room, they take time to do that, right? Now imagine you're dealing with a string that's 1,000,000 characters long. You're going to put 1,000,000 things onto your stack. Eventually, you're going to run out of space for your stack, and your program's going to crash. Also, it takes a long time to push 1,000,000 characters onto the stack. It's far more efficient just to pass in, here's the memory address you need to go look at, and then count down 1,000,000 characters till you get to the null byte. There's another thing that works this way. Which is a struct. So we can declare our struct like that. Now, when we declare a struct this way, what we're saying is that this is a local variable, therefore it's allocated on the stack. Now, this is 8 bits, one cell, this is another cell, this is 2 more cells. So what we're saying is, just reset my memory here for a second. Clean up on aisle 5. What do I call the structure? I call the structure bar. Now I'm going to label these as A, B, A, B, C, and D. So this, how we access the fields is we'd say bar.a is assigned 7, bar.b is assigned 9, bar.c is assigned 256. So remember, an 8-bit value can only hold between 0 and 255. A 16-bit can hold much more, so it can hold 256. So that's how we allocate these. So what this looks like in memory is that this is bar.a. This is bar.b. This is bar.c, and it's the A part of C. And we can be consistent here that this is the A part. There is only the A part. Right, that's that A up here. Good grief. bar.c part B. Right, so that's how the compiler lays things out in memory, essentially. It's free to do other things, but that's a simple version of it. So what winds up being in this memory is this was 7, this was 9, and I'm going to be really simple here. This is 255 and this is 1, which is how we get to 256. I'm totally lying. Don't get mad at me. I'm oversimplifying, but you get the idea. So when the compiler, or when something goes to look at this memory, it can't just look at this piece and this piece independently. It has to look at them together. It has to add the 255 and the 1 and say, oh, that's 256. Totally not how it really does it, but for simplicity's sake, let's say it is. So now if we have a function, if we pass it like this, essentially what's going to happen is that it's going to have to make a copy. It's going to make a val now will be here. So this will be, I'm just going to copy all this. It'll be simpler. Right. So this part here is copied onto the stack, same as this part here. Right? That's very expensive. We don't want to do that. That's not good. Right? So we don't want to do this. What we want to do is pass in the address of bar. So this now takes a pointer. And now, these things here, where did I say memory started at 8. These things here, sorry, I don't have to do that. I just have to say that this now points to, sorry, I skipped ahead in my head. I just have to say that this one here points to 0x01. And this becomes val. Because val is a pointer. A pointer just points to some other part of memory, right? So it's pointing to memory location 1. So now when I go to access, vals A, something like that. What we're saying is, when I say vals A, what I'm saying is go to memory location 1, which is A. So really, val A is val 0, and this is val 1, and this is val 2. So val 0 is here, val 1 is here, val 2 is here. Okay. So when I say change vals A, I'm referring to this one here, and it says make that 11. Make this one 13, and make this 257. Right. So we're actually changing that memory location. Those values, when we come back here, will have changed. So they were 7, 9, and 256. Afterwards, they'll be 11, 12, and 257. So we're able to make changes. When we pass it not as a pointer and we make a copy, any changes we make, we'd be making to the other part of memory, and that those changes will get lost. Okay? So that's all that happens when we declare a pointer, is that we say, hey, it's going to point at some other part of memory. That could be part of the heap, that could be part of the stack. And we access that through the ampersand. We can also do something like this. We can say inside of our function, we can declare this to be a pointer instead. Now this will probably crash. And it does. Why? Because what we've said is, I'm just going to reset my memory again. Strange. What we've said is that this memory location here is bar. Okay? That's bar. Bar. And it's pointing to some random piece of memory, probably not in any memory that we own. It's random. There's a good chance that it's outside of our memory space. So that's why it's crashing, because we never allocated this. So what we have to say is bar is assigned malloc size of bar. Size of struct bar. Struct foo. Good grief. Struct foo. Right. So that will allocate enough memory for a struct foo. Well, that means we need to allocate 1, 2, 3, 4 cells. So it comes into the heap, which starts at 7, and it says, okay, you're going to become A, B, and C0, or CA, and CB. And again, for consistency, I'll put the A's there. And then this says I'm going to point at 0x07. So now when we say bar, we're actually referring to this memory location here. When we didn't do the malloc, it was pointing to some random memory location. When we didn't do the malloc and we just allocated it on the stack, we declared it to be just right there. Okay? So it depends on what you want to do. Quite often, you will not bother mallocing these. There's a couple of cases why you might do that. One, this is not going to, so this is going to live for the entire length of our program. You should remember to free it. But this is going to live for the entire length of our program. There's no point in time where it disappears. So there's no reason to malloc it, because the reason we malloc things is generally for transient things in this case. So it's something that we want to have live for a little while but disappear. So we might later on say we want a free bar, set it to null, and then continue on with a whole bunch of other code, right? Pages and pages and pages of code. And we don't need bar after that. So why are we taking up memory? So if it's for the entire length of the program, there's no point in mallocing it. We can just declare it not to be a pointer. If it does have a limited lifespan, then we would do it that way. The other reason why we want to declare it to be a pointer is potentially where we're assigning it one of multiple things and we don't know which one, and there are various sizes and all this kind of fun stuff. So when you have a variable but you don't know exactly what's going into it, like a string, right? I could make my string hold 1,000 characters because one of my strings could be 1,000 but all the others could be 5. Why, if most of them are 5, am I taking up 1,000 characters? Right? Maybe there's some range between 0 and 1,000 characters. So I want to figure out, oh, this time when I run my program, the array needs to be this large. So I'll do a malloc on it for that size. Next time, it's a completely different size. Right? Maybe the user is passing in some value on the command line, and we don't know how big that's going to be. So we have to dynamically allocate it. So that's the other reason why you'd use pointers. I think that that kind of covers it. Anyone have any questions at all on anything? Oh, that actually, sorry. There's one other thing. There's the program valgrind, um, which I'm not set up to show right now, but valgrind, which will tell you if you do something like use memory that hasn't been initialized, or walk past the end of one piece of memory onto another piece of memory, or forget to free memory, right? So it'll warn you about all sorts of memory issues. So it's not a bad idea if you're on Linux to just run valgrind as a matter of course while you're developing and see what goes on. And the sooner you fix your issues, the better. The best place to fix your issues is by setting your compiler warnings so that it tells you, hey, you're using this value without it being allocated. It'll tell you that, right? Cool. If you don't do that, your program's going to crash. Hopefully all the time, but worse, it could crash randomly. We don't want that. The other thing is that you might have something where you overwrite the memory or something like that, and you don't know why your program's misbehaving. Right? So if you have valgrind running, you'll check that. So compiler first, it tells you, hey, don't even bother running this. You've got mistakes. Valgrind will help you find the mistakes that the compiler didn't catch. Right? The compiler can't check if you allocated enough room for the null byte at the end of the string. Right? The compiler's not that smart. Valgrind will tell you if you didn't allocate the null byte at the end of the string and you wrote null afterwards and trash some other piece of memory. Right? You don't want to do that. So, any questions? Weirdest live streaming ever, but yeah. Okay, then I'm gonna go. Have a good day.